Hi, how are you? Not too bad. I'm just downstairs. Oh, hey, Barb. How are you? Yeah, I really appreciate.
Just don't jump anything.
I really appreciate you guys taking the time to show me around.
Sure. Yeah.
It's a really big honor.
Yes,
So-
very quickly.
I think so. Yeah.
Yeah. So, thanks. What is this thing, and what is the research that you do here, and what is the
Basically,
purpose?
what this guy does is, in general, it counts atoms.
Oh, okay.
So it doesn't split atoms or anything like that, but it counts atoms. 3 megavolt machine. Yeah. Only one in Canada.
3 million volts.
3 million volts.
Okay.
It's on right now.
Is it? Okay.
But we use that, an example, like right now we're running what we call C14, so we're running carbon dating right now as we speak. So when it comes out at the end, which we'll show you later, we'll do the run around of the machine, it counts these little particles of C14.
So you can count isotopes?
Correct. Well, we count the atoms of that particular isotope, and with a scale, there's a mathematical equation obviously behind all this, and it shows us what date, pretty much close to 10 years about the threshold of how close that age is of that particular sample. I'm just guessing. Basically, my role here is to make sure this machine is working well. I'm the one who fixes it. Barbara is actually the scientist. Barbara is actually the scientist. I'm no scientist. So she's one of the scientists that we have.
And what is the type of research that you're doing here? What are you guys trying to, Barb? What are you guys trying to?
My unit is basically, it analyzes actinides, elements,
Actinides,
like the last line of periodic table.
Okay, yeah,
The last line.
way down in the.
I have in my phone. I don't know if you can see. So the last line, actinide series.
All these weird ones that.
These weird guys.
These are all.
The bad
Sorry,
boys.
it's a little bit dirty, but.
Right, all these
Yeah.
strange ones down here that nobody ever sees or knows about.
Yeah, pretty much.
Pretty much you know uranium, right?
Uranium.
Have you heard about it? And the nuclear
Plutonium.
power.
Plutonium, okay.
Plutonium, thorium. You may know these guys, right?
Yeah, exactly. Okay,
So these are here, they are stable. This form here, the periodic table, they are stable isotopes. But
okay.
after reactions and nuclear fission, all that stuff, it becomes radioactive.
Right.
So that thing on the chart on the floor, it actually shows how many isotopes one stable isotope can have it.
So on this table, what you see in black are the stable isotopes.
Yeah.
These are stable, they don't decay or anything like that.
Okay.
The others decay.
Yeah, the others after that decays.
Okay, so the uranium, for example,
238, for example,
238.
is natural.
That's the naturally occurring
Yes.
in the Earth's crust. Okay.
Yeah,
So
238.
what are all these then? These are ones in the black are the naturally occurring elements.
Yes.
So uranium 238, 235, 234.
233.
So why are these ones different colored then?
Yeah,
Why are these
Depends on their half-life.
okay.
Okay, so
So
they're-
the second line is the half-life. How many years they are in the atmosphere?
why are these different color though?
I think it's the degree of the half-life.
Okay,
Okay, so the black ones are stable,
these are stable, right?
but these decay.
Okay, so these are radioactive.
Yeah, now depending on the color, it depends on how fast they decay.
For example, this one is seconds. Neptune 228, 227.
Yeah. You go from
Seconds.
you actually go from nanoseconds to
Million
thousands and thousands and millions of
Million
years.
Right, so if you look at uranium, that's stable. This one's radioactive. It has a half-life of what? Is this the number of the half-life? Or?
Yeah, 10 times 5.
Oh, 5 years.
10 times 5. So put a bunch of zeros after.
Oh, okay, so how long would this... I still don't know.
That's all right.
That's right.
Okay, so E is
Well,
times 10.
Let's choose this one
The one,
first.
4 days.
So this is 4.2 days that this one lasts.
Okay.
So basically, what we call a half-life is basically you have the element,
Yeah.
And then its life is cut in half.
Right.
And then that half is half, and then half. So that's why we call it half-life.
Decays, it loses energy.
Okay. Oh, it loses energy, and it becomes so. This uranium-232 decays into 231.
Not necessarily.
Oh.
Oh,
okay.
not necessarily. No.
Yes, everyone has a different decay chain.
Yeah.
It's not here.
Oh,
You have
okay.
if you Google one of them, you can see the decay chain. So every time it loses a half-life, it emits energy. And that's we are concerned because this energy could be hurt.
Oh, okay, I got you.
Could
Right
be
on.
alpha, gamma, beta.
Okay, so and it's primarily okay. So there's 3 types: alpha, beta, and gamma.
Yes.
And how what type of radio or do they are they emitting all those types of particles, or is it just primarily alpha?
No, you see the little there is the ear, and then this is what it's emitting.
Ah,
This is
I see.
beta.
So that's beta, yeah.
Okay, I gotcha.
Yeah.
So this one here, uranium-237, 6.75 days.
Yeah.
So it splits in half.
It splits in
in
half. What's this number here?
That's a good question, actually. That one is a good question.
Forget anything.
And then okay, it's
That's beta, yeah.
emitting beta.
Emitting beta. Yeah.
Okay, so I never knew there's so many different types.
Oh, there's
of,
different, yeah.
Yeah, different types of decay energy. Yeah. But basically alpha, beta, gamma.
So why is this on the floor? Is this primarily is there a functional reason for that?
Well, the reason why, well, just the size of it, we couldn't put it on the wall.
Oh yeah.
That's one thing. It's actually true. And actually, it goes on. Actually,
Does it?
It keeps going on. But this machine here, we start with tritium at the way beginning, which is almost zero, to plutonium. Oh, sorry, uranium. Yeah, plutonium is over there. So this is what we can do with the machine. Basically, almost all this.
Okay, so the machine can measure the energy emitted from
the decay. Well, we always look at the radioactive ones, obviously, like carbon. So you got the basic one is carbon-12 that we have everywhere, obviously.
Yes.
Which is a big abundant, which is way over there, and then we got carbon-13, which is very little. It's one. So carbon-12 is 90. Oh, let's go look.
Because I'm not the carbon specialist, so I'm the actionite.
Right. I'll do the carbon part.
Okay.
So we got carbon-12, carbon-13. So these are stable in nature. So this contains 98.9%. Okay, I was close. I was going to say that.
So 98.9% of the carbon you find in nature is
12.
Is carbon-12.
Correct.
Yeah.
Then you got carbon-13, which is 1.1.
Okay.
And then you got carbon-14, which this one's the radioactive one. This is the one we use to count how old the sample is.
I see. So depending on the amount of energy beta emission from a sample, you can determine how old something is.
Correct.
Okay.
So like this one, its half-life is 5,730. So in 5,730 years, it'll split in two. And then in two, and then in two. So that's how it works.
And so, for instance, the human bones would have a certain amount of C14 in them.
I think so. I think the human bones should, because we actually do bones and.
Yes, we date like dinosaurs. How many years?
And that would be how you would date a dinosaur bone, correct? Primarily.
Yeah, but our machine only dates to about 70,000 years. But that would take another machine to do that. Okay. Since we're talking about samples, so we do bones, we do trees, we actually do water also, and rocks.
Okay.
So for C14, it's pretty much, well, obviously it's nature. So everything that's nature,
right,
that we can analyze.
Okay, so there's a lot of carbon dating happening here.
Oh my God, yes.
Oh yeah.
And do you get samples from all over the world, or
all over?
Where? Okay. And who decides what sample? I would imagine it costs a lot of money to maintain this machine. So who decides what samples? Is there a schedule? Like you have scheduled?
Yes, on all counts.
Okay.
So basically, to run this machine, just for the power itself, it's quite expensive.
Okay.
But we have a contract with the university, so that's great. But when it comes for sampling, we do have what we call preparation labs upstairs on the 4th floor. and we have colleagues there that they decide, you know, they're the one who gets the call, they're the one who makes all the plans for that.
Let's say I'm a private company in the private sector and I want some carbon dating done. Would that be something that you guys would do and they would pay for?
Absolutely.
Okay, so you guys do a lot of, so you guys would do a lot of samples, well, not a lot, but I would imagine some of it is research and some of it is commercial.
Yes, absolutely.
What is the machine running now?
Like right now, we're actually doing C14.
And what is the sample that we're looking at now?
I don't know.
The guys upstairs, they know, yeah.
Bummer.
He just received the list with the code, and from there we don't know.
But you can't physically see what it is? Is it like a powder or what?
Oh, yeah.
It's always a powder. So no matter what it is, it's always a powder, and you have no idea what it is because it's all the same color.
Okay.
So it's this blackish, which we'll show you in a couple of minutes.
Okay.
But yeah, it doesn't say, oh, it's brown. No, it's always black. It's like almost looking like a charcoal kind of color.
Okay, so it's not like you're putting like a dinosaur bone in the machine.
No.
Okay,
There's a
so
lot of preparation.
okay, so it's some kind of an oxide or something that you're putting in there.
Absolutely.
Okay.
That's not my case. We get the sample and transform in iron oxide, and then we mix with some metal bone to make a target. I can show you later.
Okay.
Yeah.
And is that okay? That's what you do then.
Yeah.
You're all about preparing. That's why you're the chemist,
Yeah.
and
Right.
you prepare the samples.
Yeah.
Understand? Okay, I'm starting to make sense.
Does it make sense? Okay, it's confusing. I know. It's complex.
It's a big procedure when we get the samples in. Depending if the person who sends it in or whoever it is, if they prepare the sample or we prepare the sample.
That is true. Yeah.
So-
Sometimes
Okay.
they prepare in the lab,
Yeah.
they send to us ready to go, and we just prepare the little stuff.
And
And for us to run, it has to be prepared in a certain way,
Exactly.
obviously, so that this guy can read it.
okay, I'm starting to get this. So we do some carbon stuff here, and then
We do.
all of this. It's basically
We pretty much do all of what's on the periodic table.
okay.
We pretty much do all of that, which is special to this machine, because usually most of the machine, this type of machine in the world, is basically doing one thing, and most of them is carbon dating. But this one, we set it up so that we can do pretty much the whole periodic table, all the way up to uranium.
Okay, so each machine is sort of tuned to
It's
do.
totally different from one to the other.
Okay,
Yeah,
okay.
it's tuned to whatever the scientist is looking for.
Right,
But
right.
for us, we decided to be quite broad. So, like Barbie, example, she does iodine, she does all the uranium stuff, and so really cool stuff actually.
Okay,
Bring it to here because the lab is not presentable.
okay.
Wow,
No, it's not presentable.
it's a lab.
No, no,
It's a lab. Yeah, it's a lab.
I guarantee you it's cleaner than my garage. So
We could show you actually where we press some samples. that would be interesting.
yeah, for sure. All of
Get
this.
in the room, but just turn to the right. Ignore the left.
This is another machine.
We are cleaning up things.
Jesus.
We are not that messy. But turn it here. Just focus here. Ignore your, yeah. So I was actually this morning preparing my samples. I'm gonna run this afternoon. Just
this
a
is
few
awesome.
tests that I need to do. So let me put some gloves.
Wow, man.
No,
Wow, you guys do some cool stuff, man. This is awesome.
Oh, that's
Okay,
awesome.
so this is what we're looking at here. Is this what goes into the machine right here?
This is correct. This is the wheel. We call it the wheel, and it holds 200 samples. Now, when I say samples, it's a mixture of blanks, just to make sure the background's okay. And so when you're running, you really want your background to be very flat and very stable.
So
Because if your blank is going up and down like that, obviously the results will just vary
all
like
over
crazy.
the place. Yeah.
So we have blanks in there, we have references in there, and we got the samples.
You use the blanks as a sort of zero, like a calibration,
zero, yeah,
a
exactly.
calibrate.
Isotope there.
I
Just the
see.
chemicals. For
Yeah.
example, this week I want to make a test for my actinize to see the machine is running okay.
Ah, I see.
So I get the tap water, I put some spike, some standards that I need, uranium 233, plutonium 242. I spike before.
In the
from
water.
In the water.
You'll put like like an eye drop of uranium in there?
Yeah, it was a drop actually.
Okay.
It's a few microliters, yeah. Mixed with another chemicals, and I made iron oxide from there.
Okay, I
I
got you.
precipitate and I dry. So this is the leftover. I don't know if you can see something.
Yeah, I see.
So it's a
some black.
brownish. If I crush it, it's gonna be like a brownish, not that dark.
Yeah, I see it brown, sort of,
Yeah, if
like a residue,
yes,
and some black residue
if
as
I
well.
crush it, it's gonna be more brown, like a fall color, something like that, brownish color. Anyways,
So that's dried. So that's your iron oxide and
as is, yeah,
uranium.
yes. And as you said, I prepared the blank without the spikes,
Yeah.
right? And then I mix with a metal bond because the machine reads current. So we need
Sorry, metal what?
metal powder
Okay.
to make a current. So it has my sample has to make a bond with the metal
Oh, a
to
bond.
create
Okay.
a current, and then you can read each target of the
Sorry,
current, like electrical current.
Like a,
current.
current.
Yeah.
Okay, sorry.
That's okay.
Sorry,
it's hard
brother.
to speak with this.
I know.
It's
Okay,
hard
so
with- yeah.
my
I
accent
see.
doesn't have- yeah.
Okay, so current. Okay.
Yes. So I mix with lead chloride in this case.
Lead. Okay.
Lead. I wanted the lead, and then became like, because lead is white, and then became like
Yes.
this. So I mix.
So Okay.
Yeah.
So lead, and then you mix it with your metal powder.
Yeah, I put the lead here,
Okay. Yeah.
and then I mix, and then I just prepare the little
So what are that?
part.
Okay.
the target. We call target. We literally press it.
And it's pressed. There's some kind of a pellet, in a metal pellet in the front of that thing.
Yes, and the bottom. I textbook. Yeah, all right. So we put a little pin
Okay, I see.
at the bottom,
Yeah.
and then we fill with the sample with a little pipette,
Yes.
and then we put like a bowl, and then we press with this guy.
You press it
Yeah,
with.
this is the pressing.
Okay, I see. Okay, so you press it into a little pellet in the front of that thing,
Yes.
and then it goes onto
And goes to the base. It calls base.
what? Sorry, what do you call that?
Base.
The
Target
base.
base.
Okay. Oh, I see. Okay.
Yes.
So this is your, and then that's the sample screws onto the top of that thing.
Correct.
Yes. This. What was it? So when I just screw it like this, I touch with our tool developed by Norm.
What's that? Oh,
It's not
that's.
patent, but it's,
Oh, it's
Yeah.
a wrench. It's a wrench.
It's a Norm's tool.
Yeah.
Did you
it's
make
a
that?
Norm's tool.
Did you make that, Norm?
I redesigned it. The
Okay.
original one wasn't doing
No,
anything.
not functioning. Yeah. Sometimes we do that. The manufacturer sends like crazy stuff, and then we have to redo it.
Yeah.
And that's it.
So there is a manufacturer somewhere in the world that makes all this stuff?
Oh yeah.
Oh, absolutely.
Oh,
You can
really?
Google high voltage.
It's high voltage,
The
yeah.
name of the little brand, the big H at the brand. I will show you.
The brand
I'll
of
show
the,
you when we get there.
Yeah,
It's,
yeah.
the company is called High Voltage?
It's High
Yes.
Voltage Engineering.
Okay.
They're in Sweden, not in Sweden. They're in
Where is it
Netherlands.
again? Europe, somebody.
Oh, this is great, guys, and this is so cool.
So
yeah.
something I want also to
Yeah.
show, if that's okay.
Yeah.
So these bottom, these bases, in this particular instance, one of our head scientists, which is Chalet, you'll probably see him later, he redesigned this top part. This used to be pure stainless steel, but we found out with the copper, it keeps it cool. Because inside the machine, when it's hit with cesium, and we'll show you that later, this heats like crazy. Like it's 1,400 something Celsius.
Really?
So we did a lot of research. We did a lot
Really?
of.
Sorry, 1,000
Oh yeah,
Celsius?
yeah. Oh yeah.
How does it not
Oh,
melt?
yeah. Well, that's the thing. So, well, it takes more than that to melt stainless.
Does
steel.
it? Okay.
Same thing with copper. But the thing is, with copper, it's got this coolness to it. Coolness, I like that. but it's true. It's much cooler than a stainless steel. Stainless steel will stay hot for quite some time.
Okay.
Copper cools everything down quickly.
It's a good dissipates of heat.
Exactly. It dissipates the heat much better than
That's-
what stainless steel would do.
Right. That's why they use it in heat sinks and all that
Absolutely,
kind of stuff.
yeah.
Right.
This is one more.
Well, that's one of them.
Okay.
Well, this is a gas one, but
This is
you can tell because there's little holes on it.
Oh yeah, that's
But that's for gas. But
And
it's
that's-
kind of the same kind of
that's the
principle.
older style.
Very old style.
Stainless.
Yeah, it should be like all stainless, but we found out with this it's perfect, and yeah, it gives much better heat dissipation and all that. Also, it's a special stainless steel. It has, let's say, magnetic properties, because in this guy, there's little magnets. Every hole has a little magnet inside, and if you look, you can see like where these little holes are at the bottom. You can see there's a like
I
a
see that.
grayish color kind of thing.
Yeah, I see that.
Well, those are magnets.
Okay.
So if I do this, you can see the magnets. All the little holes are magnets, and so it's held in there because actually this thing will go this way inside the machine,
Right,
and we'll show you that
right.
later.
And does it turn?
Oh yeah, it turns.
Okay,
Oh,
so
yeah.
it turns to aim the samples, I guess,
Exactly.
into the
So
beam.
it's 50 samples. So this is number one. Usually we have what we
they're
call a park, which is not in there right now because we'll take it out of the other one.
Okay, they're numbered too.
Oh, they're all
Oh, yeah,
numbered.
they're numbered.
So it's 1 to 50, and then this is 51, 101, and 151.
Okay, okay,
So
200 position, right?
it's a 200 position, yeah.
okay. So some of these would be samples, some of them would be calibrating. Like you wouldn't necessarily have like sample. You
Yeah.
probably have sample.
Well, sometimes you have like 5 or 6 samples in a row, and then you have a reference,
and then a reference.
and
Okay.
then,
Okay, so
and
this
or
is
a
the
blank.
reference.
Yeah,
Yeah.
that's
So-
the reference.
Okay.
That's my reference material that I know the concentration of atom, the isotopes that I want to analyze.
Okay.
Yeah.
Okay.
Does it make sense?
Now,
Interesting.
usually, of course, there's international references that's known around the world, but we've also have some that we ran, and these you have to run, I mean, a lot to make sure that it is stable all the time, and then we can use it as a reference.
Okay.
But there is international references that's well known in the world.
Yeah, exactly.
So this
That's
is
one of them.
okay. So certified reference material.
Absolutely.
Okay, International Atomic Energy Agency.
Yeah, it's the
Analytical
agency.
quality control. Interesting.
Oh, it's all quoted. Yeah.
Yeah.
So you're not just that just doesn't go on like the Canada Post or like UPS.
we need
No,
it.
no.
It's a paperwork.
Yeah. So that's
Specially delivered.
It's a special delivery. I'm gonna cover this.
Yep.
I'm gonna put in the afternoon. Any more questions?
sorry.
Any more questions?
No, no.
I'm just gonna cover.
I'm loving the aluminum foil though.
Oh yeah.
This is
Well, it goes in the microwave. No.
so you're coming out of here now with some samples. Cool.
At one point in time, this is our newest machine that we're getting ready.
Okay.
So this guy only does carbon. It's only for carbon dating, that's it.
Okay.
The reason why we got this is because we have so much carbon dating on the big guy that we barely have time to do scientific work like
Right.
research and stuff.
Right.
So then we decided to buy a new machine. This will take care of the C14,
Right.
which
Okay.
we have more time now on the big guy to do some research.
Makes sense. What's
Absolutely.
I'm just noticing right now we're standing underneath a huge crane.
This is my baby.
Oh yeah, another one.
This is my dad. This is my baby. Obviously, we need a 10-ton crane in here,
That's
which is kind of weird in the lab, but thank God we have it.
But what do you so what do you use that for?
For lifting heavy stuff.
Okay.
Now, as you can see, in this lab, we don't have small stuff. We
No.
have big, heavy magnets and a whole bunch of different
Shield.
things.
Lead shield. It's
Yeah.
a lead shield.
That's a lead shield.
Which one? What is?
Both of them.
These here?
Yep. These are gamma specs.
Only because there is nothing wrong running. So it's all lead.
No way.
Yeah. For
What?
it reads the gamma.
Okay, so this is a solid piece of lead.
You can
Or
It's
the top too? is-
everything.
Everything. The
You're
whole thing.
kidding.
Oh yeah, the whole thing.
You can I think that it's empty here. The copper shiny just took over, but everything
So
is
it's like a sputtered copper.
it just took over. It's like a
This whole thing is lead.
yes.
What?
Pretty heavy, no?
Oh yeah.
How
So
much?
we need the crane.
How much would that weigh then?
That's a couple of tons easily.
Yeah.
I don't remember how much that one weighs.
So what do you put in there? What do you put in this
Actually,
thing?
this is Barb's other
Baby.
venture.
What goes in there?
It's a detector, just for gamma. I
Okay,
analyze gamma, and what I do, I just drop a sample. Okay, this is standard.
And you would need the crane to lift that. To put it.
No.
When we need,
When we need to repair this or whatever, we use the crane because we have to lift it up.
Oh, I
That's what
see.
happened with this guy.
yeah, it's pretty heavy. The detector is pretty heavy. So I put a sample, like it's a standard. So I leave it here.
Okay.
I leave it there for a day at least, because it counts two per second.
So what's cool also, you can probably mention the crystal.
Yeah, there's a germanium detector.
Sorry?
It's a
Not exactly true, but not far.
germanium detector.
It is, yeah.
Yeah.
There's actually a crystal, which is the detector, but it's a very well carved crystal they use inside of this, and that one too.
It's lead because presumably you're.
It's high gamma,
And we need a
very radioactive.
So.
No, not radioactive. Sorry.
No, this lab is empty quantity. We don't have like heavy radioactive stuff.
Okay.
But the shield is to not, because it's very sensitive detector, so it captures everything
I see. So
from everywhere.
what you're trying to do here is keep radiation, background radiation out instead of keeping it.
Yeah,
you're
actually,
trying
it's the other way
It's the
around.
other because I was thinking, well, why are we putting that if it? Okay, I had it backwards. I was thinking you were putting highly radioactive things in there, but
No, well, it's not, yeah, it's not highly radioactive, but it's to protect it from outside radiation,
It's
Because
to-
you can get
from
everything.
any interference that we have.
yeah, okay.
You bombard you from everything.
Exactly. Okay, so it's like a Faraday shield for radiation.
Yeah, yeah.
Exactly.
Yeah.
You got it.
Yeah.
Okay. So what's underneath there then? What's the?
That's full of liquid
The
nitrogen.
liquid nitrogen, because it gets hot. If it's too hot, I can lose the detector. So I
So
have
it's to keep it cool. Keep the detector cool.
Keep that cool?
Yes.
Yeah.
The detector has
The
to be
detector
cool.
inside, yeah.
Oh.
So the detector is actually sitting in there.
And,
Well, I
and,
mean, part of it is sitting in there.
and why does it need to be cool?
Because of the, well, the
It's a semiconductor. So when
I see.
we turn on, it goes, the electron goes back and forth, it dissipates heat,
Right.
right? So everything gets
Gotcha.
hot.
Yeah.
very hot.
And if it's too hot, the electron goes and doesn't come back. And then I lose the detector.
So it's kind of like, so you're trying to keep it cool to keep the resistance down.
Exactly. So you can tell if we're using liquid nitrogen, as you know, it's like minus 276 degrees or something like that.
Yeah.
Yeah.
So it's hidden, unfortunately, you cannot see it. So this part is the crystal somewhere here. And we only have
okay.
a cup to hold the sample. And
Okay, I see.
unfortunately it's hidden, you cannot see.
Yeah. Okay. So there's a crystal in there,
Yep.
finely tuned crystal that detects the
So-
gamma.
Exactly. So we did have an incident where the detector got damaged, which is why this one is not operational right now.
Okay.
So yeah, obviously I needed the crane to take this out because it weighed a couple of 100 pounds. So
Yeah, yeah.
we took it out and
At least.
we sent it off. So we need to send it off to the company because there's no way to calibrate this thing ourselves. So they have this special way of doing it, very very special and sensitive, especially for that crystal.
Okay.
So we can't do that here. So obviously we have to send it back to get it repaired.
Wow.
Which reminds me, any news on that guy?
I'm working on it.
Okay.
You know.
Complicated.
Yeah.
You got, oh, I see. I see right here.
Yeah.
Okay. So you're looking at this peak here. This is a spectrum.
Yeah, this is my background, all the background going, and then I see this peak, which is in the sample. I'm expecting to find something because it's reference material.
And what is this peak indicating? Is it, this is gamma radiation.
Sorry. Hello.
Is this a spectrum we're looking at right here? Or?
Yeah, the spectrum. Oh, no. No. If I see a Hang on.
Oh, I see.
Yeah.
So it tells you.
Tells you this, and the software is basic. It doesn't tell you right away the activity. But I have the gross area, I have the energy, I have these details, and then I calculate later what's the activity of that peak.
Okay, count rate.
Yeah.
Okay.
Does make sense, right?
Wow. Really
Come back
interesting.
to the
Okay, so probably the next time we'll talk about this guy, but for now,
Sure.
yeah. So this is a research line that we're working on. We're just going to bypass this quickly, but it's just
Sure.
it's a research line in progress
Okay.
that we're working on right now, which is hooked up to the big guy.
This is hooked up?
Yep, it's hooked up to the big machine. But it can also work on itself. So it could be just working independently from the machine, or we could use a machine.
Okay.
So depending on what we're doing.
What are we listening to right now?
Oh, it's just cooling off the cesium.
Oh, okay.
They stopped the run. So
Oh.
the run's over. Actually, I think you might be able to see it come out of there. But yeah, actually Barb's gonna take it out and probably put hers in. So you'll see what it looks like when it's
Oh,
loaded.
okay. Awesome.
That's a good thing.
Cool.
So, are we gonna do that?
They are in the phone. They are talking the phone.
Yeah, if you guys need to take a break, just let me know. You guys got stuff to do.
Mommy can go explaining.
You want me to go around?
Yeah.
I think he wants to.
Give me 1 second. I'm just
Sure.
gonna go see how long it's gonna take before we can open her up.
Okay. Cool.
I have time enough to go around the machine. It'll take about 20 minutes.
Okay. Perfect.
And then once we're done, we can come back here and you can see how we load and all that.
Sure. Awesome. I really appreciate your time.
Sure.
Big time.
I love to show off my machine.
I would too, man. For sure.
All right. This may bug the sound, I guess.
No. We're
Yeah?
good.
Okay. So what you're hearing now is we just finished a carbon run. So what we're doing now is cooling off the cesium. And I'll explain to you the cesium, what exactly it does. It's very an important element to our machine. But first, I'll start off by starting at the beginning.
Sure.
Let's start with that. So we got the sample and all that, right? And we got our lower solder sitting on our base. So this is the, well, again, it's one of the gas one because you can tell with the hole there. But so we had this on our thing. We load it in here.
Oh, I see.
So what it does is, so it's sitting upwards, obviously like that.
Yeah.
And we have a piston that goes in the back, which that's why you saw the holes in the back there. It pushes
I see.
the rod inside what we call the source. So we have one here. This is the old source that we had in there. So this is what we call the version B source. Now we have a version C, which is quite a step up from this guy.
Okay.
So we had that done early, not this year, last year. But the principle is the same. So what we have in a source is basically, we have this guy. And what this guy is, if I can do it, almost. Come on. Yes, no, maybe. Almost there. Okay, got it. So this stays the same. So this guy here is what we call the boiler. This is what is filled with cesium inside of that. We have 5 grams of cesium that is in there. And so this goes right there. I'm just going to put this back together quickly. This is our show and tell, so it's all good. But we actually use this for many, many years.
Okay.
So this goes
all right.
like that. So this goes like that. And when it goes in, So you have this little guy here, which is called a shroud. So the cesium rod goes into the shroud, like that.
Yeah. There you go. I see, yeah.
So inside that shroud, there's 6 little holes. And they're kind of a beveled kind of way where when the cesium comes in here, it's gas. So it's a cesium vapor. And we use, and that's concentrated and it's pushed into these little holes, which creates a cone kind of spray, if you will.
Okay.
Okay?
Yeah.
So it's kind of like that. Like all 6 of them goes into this one area where it drills inside the sample.
Okay, so it's injecting cesium vapor into the sample.
Exactly. But the cesium is...
and this is for the gas. This is for the gas sample.
No. Never mind the gas sample.
Oh, okay.
This is just a body, but
okay.
no, it takes the sample and pulls out the ions and everything else from the sample. So
okay.
all the particles and everything comes out. So it's a positive beam that hits this and it pulls everything out. So it kind of like, it drills and everything just floats around and gets pumped, not really pumped out, but it comes out. And what it does is, everything comes out, so everything on this side before the tank, everything is a negative ion. Okay, that's very important because I'll show you why later. So everything that comes out of this is negative ion. So what happened was, once everything's in place, this pushes the target inside, and then it comes into this little aperture right there.
Right.
Gets bombarded with cesium. Particles comes out, and then comes out this way. So it comes out going that way in the machine. So everything comes out on the back.
Okay, I see. Everything comes out on the back here.
It comes out of here, and then it starts its merry way. So if you look at the machine, it gets bombarded. So the cesium, like that, it gets bombarded. Particles are coming out this way. Okay, so this is actually sitting at, well, for us, it's sitting at 35,000 volts.
Wow.
Yeah. So this little guy here is at 28, and there's a 7 also kilovolt. That helps kind of like pushing everything. So everything in this unit is pretty much current. You got voltage and you got current.
You have to use so much voltage because you're trying to direct the ions.
You try to separate. You're doing a whole bunch of stuff, which you'll see when we go through the machine. So in this particular case, this is 35,000 volts. So we're pulling negative ions. So it starts its merry own way. This guy here is an electromagnetic analyzer. Basically, it's a filter. So it helps the beam to go that way. So when I'm talking beam, I'm talking particle beam, not like a laser beam. It's a particle beam. So a whole bunch of particles, beam coming through.
It's all the particles that have just...
Everything that's in there. So you got carbon, you have nitrogen, you have a whole bunch of stuff in there. But we're looking for carbon, right? Now the thing is, the reason why this is all negative, since I said nitrogen, is because C14 and nitrogen 14 have pretty much the same mass, and you can't tell them apart, except that nitrogen cannot do negative ions. So that's why this is all negative.
Okay.
Because if it was positive, we couldn't tell nitrogen from carbon.
Right.
So that's why. So they found out back in the day, actually in the 70s, they found out that nitrogen cannot do negative ions.
Okay.
So they're like, oh. So that's how we can do carbon 14, the drive carbon 14. So this goes through, filters out some of the elements that we don't need. Goes that way to our first magnet. So that guy there is called a bouncer magnet.
Okay.
So it does 3 things. So one thing, it's a magnet. So it bends the beam to go that way. So that's one thing. The second thing is it bounces, that's why we call it a bouncer. It bounces from one element to the other. So we're looking at, in this particular case, let's say carbon, we're looking at C12, 13, and 14. So 12 would be on the inside, and always on the inside, because it's a lighter mass. 13 is a little bit heavier, he's in the middle, and 14 is heavier. So basically it's coming out kind of like that. So So 12 is coming out really quick, 13 is a little bit slower, and then 14 is slower. So they're kind of like that.
Right.
And 12 is always on the inside of the whole beam. Same thing, 13 is always in the middle. So this is the only one that we actually have 3 beams in the whole periodic table.
And you're talking about the physical mass.
Physical mass
and the reason why the 14 is on the outside is because it's heavier, the inertial.
In the mass, in the weight, yeah. But they all also have different charges. And again, so once it gets to to that bouncer, so what the bouncer does is it subtracts and adds voltages so that when it comes out of the bouncer, they all come out at the same speed. But they still have their different masses.
I see, I got you.
So they're coming out, and then of course, all these things that you see sticking out, these guys here and these guys there, these are all power supplies. So we add current or voltage to reset and realign the beam and stuff like that. So you'll see that a lot around the machine.
Okay.
Some of these are pretty much 40,000 kilovolts. Wow, sorry, 40 kilovolts.
So is that just running off your regular service, like your regular utility? Like it's a 240 volt?
Well, it's actually running off a 600 transformer, 600 volts.
Like a 3-phase?
It's a 3-phase, absolutely. It's 3-phase. Yeah.
Okay, I gotcha. So you guys have, in terms of power here, you have the standard 3-phase industrial power.
Yeah, special setup, for this guy.
Okay.
Because so the 600 goes to a 400 volt panel.
Yeah.
So we're actually running on kind of like a 400 volt system.
Okay.
Which is rare because we don't have that in North America.
Yeah, exactly.
But for this purpose, yeah. So, we got our beams are coming out, and we have all these guys here to fix the beam and put it right. We got what we call steerers. We add a certain current to them to push the beam correctly so it goes straight, so it doesn't go all over the place.
Right.
And then we enter the tank. Now this is where it gets cool.
Huh. Okay, so we got 3 beams now.
We got 3 beams and other junk that's coming with it.
Wow, man, what is all that stuff?
So it's coming through.
Okay.
And we're going inside. So this is obviously the accelerator part. This guy.
Okay. Is that just a big hollow tank?
There's some things in there. So, like this guy here, all the way in, it's all glass rings like that. So this is what's from another one. A little bit smaller, ours a little bit bigger. But we have tons of these all hooked up together with different potentiometers, different potential, so that, and it's kind of funny because when you look at it inside there's metal plates where there's a hole here and the next one is there and the next one is, so it does a spiral like that all the way through.
Okay.
And it has a certain voltage. So this part here is actually a huge transformer. This is what helps it get to 3 million volts.
Wow.
And I'll show you that in about a second. But first, this tank is filled with SF6. It's the same type of gas that they use in transformers. It's an inert gas. It helps to prevent arcing. So inside the tank.
So it's a sulfur fluoride.
It's a sulfur fluoride.
Sulfur hexafluoride.
Hexafluoride, yes.
Hexafluoride.
Exactly.
Okay.
So you're more scientist than I am.
No.
So we have 6 bars of this guy, which is closely to 92 psi.
Okay, 6 bars.
Inside this tank.
Wow. Unreal. Is that why you've got all these massive bolts here?
Yes, it's so much fun to take this apart.
It
takes mostly a day to do that.
Have you actually taken all those bolts off?
Oh yeah. And we're actually going to do it also early next year.
Wow. And that's just for maintenance? You have to get it?
Because once in a while we got to go in there and make sure everything's okay. Everything's aligned and all that.
Yeah.
Normal maintenance.
Those aren't your typical Home Depot bolts, I guess.
Oh no.
They're like probably special grade.
These are special, yeah.
You know.
And it's kind of like you got to use the same principle as you do when you do a tire on a car.
Yeah, the torque.
The cross thing.
Oh, I see.
So if I'm tightening this way, The other person on the other side has to go down the other side. So it's always crisscross because it has to come in flat.
Is there a gasket in there?
Oh yeah, yeah. There's a gasket in between.
Like a cork, like a steel gasket?
It's a steel gasket.
Okay.
Oh yeah.
Wow.
Now, this guy must seem a little familiar. It's actually a transformer.
Okay.
Same thing that you find, you know, in the
on the hydro pole.
post and stuff like that.
Yeah. Okay.
So this is a stepped up transformer. So basically, what happens is this is getting 230 volts, setting 230 volts to this guy. This brings it up to 150,000 volts.
Nice.
And then in here, there's a whole bunch of rings in there and all that. I won't get into details. But
Yeah.
it brings up the voltage to 3 million.
3 million volts.
So right now we're running at 2.5 million volts right now.
Oh my God.
All right, so
Wow.
we got our particles coming in, our negative ions.
So sorry, you'd be in a lot of trouble if that thing were ever to spring a leak.
Oh yeah. Oh yeah. That's why I got to keep an eye on it
Yeah.
every day. But no, I mean this company. I mean they've been doing this
Yeah.
for
But
ages.
3 million volts though.
Yeah, I mean
Like-
you have 250, 500, and then you got your 1 million volt. I don't know if there's a 2. There's a 3. I think there's a 4. There's a 6, an 8, a 10, a 12. Now these guys literally you can walk into. Not this one obviously, but
Yeah.
when you get to 6, I can actually almost stand inside and
Oh
walk.
my God.
It's twice the size of this piece. So let's continue the science.
Yeah.
And so we have our particles coming in, and once it hits the middle part, when it hits the high voltage, it acts like a slingshot. So basically it's like that. As soon as it hits that, it gets shoot out, which is why they call it an accelerator. But at the same time, there's a gas bottle inside of this, which is argon. And what that does is it strips an electron or 2 or 3 from the particles coming in, which everything turns into a positive.
Okay.
Yeah, it goes into a positive. Yeah.
Okay.
So now everything is positive on this side, all the way to the end.
Oh, interesting.
So when it comes out about 1/10 of the speed of light. So they're shooting out like crazy.
Oh.
So, which is why you have a ton of power supplies here to redirect, refocus, reshape the beam coming out, because they're coming out all over the place. So this is why we have all this until we get to the magnet. So apart from other garbage that's in there, we have our 3 main beams, C12, C13, C14, right? So C12 is on the inside, 13 in the middle, 14 is on the out. Then it gets into this guy. So you can tell the beam is coming inside of this.
So it's a waveguide of sorts.
See how small it is?
Yeah.
And it gets into our big guy here.
Okay, I see. Wow.
So this is our big baby, our big magnet. That's 19 tons, by the way.
Whoa.
So it's heavy.
Jesus.
Also, I have to mention, this particular magnet, actually belongs on a 6 megavolt machine. But we took this because we wanted to do uranium and plutonium, because they're very, very heavy elements. So you need a really big magnet to be able to curve those beams. So that's why we have this guy.
Okay,
So little history on that one.
Okay, so you're proud of this one, and I notice it's on shock.
It's on shock inflatable. Yeah, absolutely.
Those are airbags, I would
Correct.
assume.
Yep.
Oh my-
Very, very, very stable. It's incredible how stable this machine is. It's incredible.
Is there any kind of special stabilizations for the actual floor we're on?
Oh, yeah.
Is the building on shock absorbers?
Actually, this building, like our plate, and I'll show you later the division, but this slab that we're sitting on right now has, I think it's 2,000 steel rods going directly to the bedrock. So a couple of years ago, we had these tremors, right? I don't know if you remember that.
Yeah, I do, yeah.
We felt nothing, like zero.
Really?
But as soon as we got off this plate and we went, like, let's say like in the control room over there, we can actually feel it. Like we saw the crane move a little bit because it's on the outside walls. And we're like, what the heck's going on? And we couldn't feel a thing on this slab.
Wow.
But as soon as we got out of it, yeah, obviously we felt it.
Unreal.
So there's
So
a lot of these rods in this cement floor. Plus, it's almost 2 feet thick.
Right.
2 or 3. Yeah, almost.
So this is like, well, at least 2 feet of concrete.
It's at least 2 feet of concrete,
And-
but it's a special bond concrete.
Yeah, and vibrations are a big concern. They
Oh, yeah,
screw with the
if it
beam.
moves slightly, everything's off. Everything's absolutely off. It's amazing how precision this thing is.
And it's okay for us to walk on the floor while it's
Absolutely,
doing.
it doesn't make anything.
Oh wow.
Oh yeah, yeah.
Okay.
And that was another thing too, with the obviously with the crane. When the crane moves, that's why it's sitting on these pillars that you see. But it's not connected to this slab.
Right. Okay. So I see. So those I-beams are connected someplace else.
Well, these I-beams are sitting on a huge. That's why they're kind of square thing there.
Yeah.
They're sitting on this huge, these huge cement pylons
Oh, I see.
all the way through.
I see.
But they're not connected to this slab.
Not connected.
This slab is separated. And
Right.
I'll show you. Well, you see that little strip, that little gray strip,
Yeah.
like right there, that little gray strip going. This
Yes.
goes all the way around. Well, that's
Oh, I see.
that's where the separation is,
Oh, okay. I got
and that's
you.
all around this slab, all around the lab.
Okay.
Oh, gotta do this quick.
Yeah. We'll just do a
So
quick.
now, this is the out. So remember, when we came in, it was very little, like a very small kind of little square thing, flat square. This is the out. So what's happening is, you got your 3 beams, and they're really close together when they come in. But when they go through the magnet, they split up like that.
Okay.
When they get to this guy, we have inside of here what we call Faraday cups. They're literally these little square metallic cups, if you will. And so there's one here, well, one here, and one in the middle. So it captures the C12, C13. And we want to measure C14. So C14 keeps going through. That's why this is farther that way.
Okay.
So
I see.
C14 keeps going through, because that's the one we want. So 12, 13 stays there. And this is actually also where we do the ratios. 12 on 14, 13 on 14, and so forth. So 14 keeps going through. Again, a little bit of adjustment, blah, blah, blah. And then we have another elemental analyzer, but this one's much more powerful than the first one we saw. This one can run up to 100 kV. So when we're doing, excuse me, carbon, right now it's set to 72,000 volts.
Okay.
To be able to have the beam go through, because remember, every beam is charged. There's a particular charge to them.
Yeah.
So what happens is 14 atom goes through and everything else just hits the wall.
Okay. I
and
gotcha.
gets flushed out.
I gotcha.
So it comes out here, again, adjustable. But then it hits our last magnet, this guy, which is called a switching magnet. So basically what this guy does, and I guess you can guess what it does.
I see. Okay. I gotcha.
Now, you can have multiple outs for different
Oh, that is cool.
different project that you're doing. In this particular case, we only have one detector, but we will have more, actually.
Okay.
But now we have one. So from this point right here, all the way to the beginning, everything is under high vacuum, right? But this guy is filled with a gas called isobutane.
Okay.
So positive kind of thing. And the only thing between these two, the vacuum and the positive pressure, is this little tiny window. I don't think I have it. I know somebody took it away again. Okay. Well, anyway, it's about this big by this big, and it's literally a window. And it's the material is a not exactly a crystal, but no, it's not a crystal. It's like a sheet of what is it called again? Oh, I had it for 2 seconds. I gotta write these things down.
Like, well, is it a type of glass?
It's not exactly a glass.
Is it acrylic?
It's more of a. It is closer to a crystal kind of thing.
Okay.
It'll come back
Quartz?
to me.
Quartz?
It's not quartz, no.
Huh.
Anyway, it's very, very thin. If I have it in my hand, and if I breathe on it, it just pops.
Really?
Or if I just do that, it just pops.
Well, but how does it?
Yeah, I know. Great, huh? So it's able to handle the positive pressure against the negative vacuum, let's say.
Oh, so you're balancing the. This is positive pressure.
This is positive pressure, full of gas, and this is high
Negative.
vacuum.
Oh.
All this is high vacuum. So what's happening is that C14 is coming, so the atom is coming, So now we're down to the atom, and we give a certain potential to this window. So it's got a positive kind of charge to it, to just let the C14 go through, and everything else will supposedly be stuck.
Right, because the C14 is positively charged. Everything else
It has its own little energy.
Yeah, everything else that is, so you charge that little window positively, so it kind of like bucks
Either
off.
positive, yeah, it's positive.
It's kind of bucking off any other stuff.
Exactly, and it's letting the other one, that atom go through.
Okay.
So inside of this, it's a little like this, a little more sophisticated than this, but it's kind of like this. So when it's coming through, it's hitting one of these rods inside, and it gives an electrical charge. So when it does that, we have something like this that appears on the screen. Now this is, by the way, this is not carbon, this is actually beryllium. The principle's the same. So let's say this doesn't exist. This is what you see. So all this is all the atoms that are coming in that we call counts. And we just circle this, and then we just calculate how many there are. And then with that, there's a scale, there's a mathematical equation behind all this to calculate everything. Yeah. So this machine basically is doing this.
You're measuring a grain of sand in a desert.
About 100 kilometers square of a desert.
Oh my
This is what
Lord.
this machine can do.
Oh my.
So it can measure 1 grain of sand in 100 square kilometers.
Wow.
It's amazing what it can do. You can find your car keys easily with this.
Yeah. Wow, man.
So basically, there you go. In a nutshell, is basically.
Wow, that's I gotta have to take a nap right now.
Well, the fun part's coming. Actually, you'll see us changing the samples.
Okay.
So you'll be able to see how that looks like.
Wow.
So we should be soon.
I really want to thank you, Norm, for taking the time for
pleasure.
doing all this.
I love showing off my machine.
Oh, it's just it's awesome. It's just really, really.
So just on the record,
Yeah.
I can finally say that now, but I couldn't say that back then because you'll know why in a second. I call this machine Phoenix because it's actually this lab is from the ashes from another lab that was in Toronto for about almost 40 years, but they had to close that one down. And this one is kind of the rebirth of that lab. But this is a brand new machine, so the old machine got disassembled and all that. So that's why I call this machine Phoenix. But back in the day, when I started to call this Phoenix, we had, you know, that little Phoenix pay thing going on. So I had to be careful with that because it rubbed a lot of people the wrong way. So I didn't want to do that. But that's our name. That's Phoenix.
So you work here like every day or what?
Oh, every day.
So it's Monday to Friday?
Sometimes the weekend, sometimes the nights.
Okay.
Yeah. Well, it's my job, 24/7.
Okay. So
in case something happens, because there's a lot of things. There's a lot of different things that is helping this guy to run. One of them is water. So we have a closed loop water. That specifically is for cooling the magnets down, because obviously they heat.
Right.
So that's used to cool them down, and also this guy. We have power, we have air. So it's a lot of things that I have to take care of to make sure everything's running beautifully.
And so you're on call.
Oh yeah.
You're on call. Like, is this machine running 24 hours a day?
Yep. 24/7, man.
Because I mean, obviously, it's an expensive piece of equipment.
Oh yes.
Like the time is very valuable on this machine.
Absolutely.
So it's got to be running 24 hours.
It's nonstop. It's nonstop.
Do you have a night shift that comes in too?
No. So the way that we're set up, I was able to put an alarm on this machine. So that if something happens, it actually sends us an email.
Okay.
And then we log in using a remote application to be able to come in and see what's going on. And if it's to a point that we physically have to come in, then we just come in and fix whatever, you know.
So you panic every time an email comes in?
Oh yeah, definitely, always. But it's pretty cool. I mean, it's a pretty sturdy machine, and yeah.
Like for the most part.
For the most part.
Yeah, I mean, like
it's a machine.
Yeah,
but you know, it's got its little quirks. Oh, we're opening.
Awesome.
All right. Well, let's go there. Never mind me.
So the air the hissing noise we were listening to, what was that?
It's for cooling the cesium.
You told me that.
Okay, well, while they're doing that, because I know I have a couple of minutes to do it. So, cesium, look it up on YouTube. It's fantastic.
Cesium, yeah.
Actually, cesium is very volatile. It doesn't like humidity, doesn't like water. And it's very violent. It erupts. Like either it explodes depending if it's packed, or it just catches fire like crazy.
Is it on the same like column as potassium and?
Yes, actually it is.
Okay,
it's on that column.
Okay, so it's just like way down at the bottom.
Almost at the bottom.
So it's like super violent.
Oh yeah.
Cesium. Oh, okay.
Cesium. If you go on YouTube, you'll see what it is.
Yeah.
So what we're doing now is that we're pumping argon in that carousel.
Okay.
So there's a what we call a gate valve that closes between that and the rest of the machine, so that we're just bringing this up to air so we can open it, because it's always under vacuum.
Right. So you're bringing it up to equalize the pressure.
Exactly. So we're just pushing argon so that at one point we can open.
Okay, I see.
Well, actually, we'll go on the other side.
Yeah.
These guys need to go here. So this was the run of C14 that we just finished. So
man.
Barbara will show you how.
Wow.
Actually, next week I'm cleaning the source.
Sorry?
Next week I'm actually cleaning the source. So I'm taking the source out to clean it.
Okay, the thing that you told me, the thing that you showed me.
Yeah. So I
The
have to take the whole thing apart, clean it, and everything.
thing that injects the cesium, like the injector.
Injects the cesium, which also you also inject the target inside.
Right.
Yep. So once in a while I got to clean that.
Just a solid piece of billet aluminum,
Pretty much.
or is it
It's
stainless?
stainless.
Oh.
So she's going to load this particular little run. This one's pretty cool because it's actually for research. So we do our own little research also when we can.
So this is not your. This is not your
Not that typical
jelly bean carbon dating.
No,
this
no.
is there's some interesting stuff in here.
Oh yeah. So Chalet, that you see right there,
Yeah.
he's the brain of the operation.
Okay.
So he's the brain, I'm the bronze.
So what's he doing there? He's wiping out that.
Yeah, sometimes you have residue from the samples and stuff like that, so we have to keep everything very clean.
Right.
So now they're closing that up. They're going to close the argon, and now they're going to pump down. So you're going to hear this guy here, the gate valve will open up to vacuum. But first, this will pump down, and then this will open up to vacuum. You just heard that? That's the argon just turned off.
Okay.
And then they're going to start the pumping. So they're going to pump this area here with low vacuum, and then they're going to open up to the high vacuum.
Oh, I see.
And then at one point everything will calibrate normally.
Right. It would be a little bit too much of a shock to just like
Way too much.
pound that
Oh,
in.
absolutely.
I mean, what kind of a vacuum are we talking? Like.
Oh, we're talking like 10 to the minus 6, 7. So it's a mean vacuum.
So so that's. I mean, all these pipes we're looking at. That's why they are.
Yeah. So there's a turbo down here. There's a turbo right there. So these are exactly like turbo engines. They're basically the same.
Okay.
So it's there you go. So the roughing pump just started. These two turbos will turn on soon. Yep.
And that's why they're so thick. That's the walls.
This is super thick, yeah.
So the walls of this stainless steel pipe are like.
They're pretty, yeah. They're a good thickness. And once in a while, these turbo will die because it's a machine. So I just changed this one not too long ago.
Okay. Okay. So they've started pumping this down.
Yeah. And they're starting slowly to pump everything down.
And how long does that take?
So this will take a good couple of minutes. And then at one point, this guy will open up to the high vacuum. So this will be low vacuum, which is pumped by this little guy here.
Right, okay, I see.
So that goes to a rotary pump down there. And then once it reaches a certain -4, then this opens up to the high vacuum, and then everything will equilibrate. So it'll take a couple of minutes to equilibrate.
Is it a sort of a big noise when that thing kicks on?
Just a psh kind of thing.
Okay, I gotcha.
Yeah.
Amazing stuff, man.
Oh yeah.
I can't thank you enough.
Oh.
I can't thank you, honestly. I really appreciate it, and this is probably going to be the best video on my YouTube channel for a long time.
That's right. That's right.
Come on, guys. Well, UOttawaScotty signing out. Thanks a lot to Norm and Barb. She's over in the control room. Guys, thanks a lot for coming by here, and thanks again to Norm. UOttawaScotty signing out, and we'll see you next time. Thank you very much, Barb, for your time. I really appreciate it.
Pleasure.
And maybe sometime in next year, when you get your other machine running, we'll come back and see you guys. And yeah.
And we'll be here.
All right, guys. Take care.
Thanks. Bye.
Well, guys, that was pretty awesome. I hope you enjoyed that episode of UOttawaScotty. That was big thanks to Norm, big thanks to Barb for showing us around, showing us all the fun toys. That was a blast. I just had a riot there. Stay tuned to UOttawaScotty for more awesome stuff.
Through your fingers, still slipping but you're holding on. Dark times in the city by the river, you keep swimming till the water's gone. You can't see it when your head's in the gutter, you can't hear it with the war in the yard. One side keeps falling through the other, you can't see it 'cause you're looking too hard.